everyone. Let me turn the fan off. Sorry about that. So I wanted to do some problems for the astronomy class. There's at least two types that you've seen so far. So I'll do this, and then I'll do another video in a little bit, in a couple of days, where we talk about the problems that you're likely to see probably in week 4, where we're doing chapter 3 stuff. So the first calculation you had to do in homework 1 was about the travel time of light. And so I'm going to show you, obviously I'm not going to show you the actual problem, right? But we can get a ballpark of what the right answer might be. And I'll show you how to do that calculation. Right? So, on the one extreme, right, we're talking about Mars for the problem. So if we look at Earth, it's pretty well known that light takes about 8 minutes to get to Earth. I think we cover that in chapter 1. Right? And we also talk about how long it takes. So a way out of this problem in principle is to watch that video. And that's 45 minutes long, and it shows you light traveling at 1 light second per second. And just wait till you see Mars. But instead, what I'm going to show you is how to calculate it, and I'm going to use Jupiter. So the idea is that you go into the back of your textbook, and on page, we'll go back up. I'm looking at something else here to get the page number, and it's just jumping back. So this is on page A15, which is in the very back of the book in the appendix. This is a table that is called the orbital properties of the sun and the planets. And I looked for the distance from the sun in 10 to the 6 kilometers. Now what this means is there's 6 zeros here. This is 7, 7, 8. Here's 1 0, is this 3. That's what we have. Right. Now, the other bit that we need is when we're talking about light traveling, we have the distance that it's going to travel, right? And we can just do distance equals velocity times time. So the other bit we need is the speed of light as it travels. And we discuss this in other circumstances. I think it's in the first chapter that we talk about this, right? Because it's a first chapter problem. And you can look in there. But if you look in your other information, all right, we can get the velocity of light, which we happen to call c as a constant. And you'll look at this in your textbook. It'll be 3 times 10 to the 5 kilometers per second. Right? And this is on page A2, if you're looking for this. So we have these two numbers, and this is the thing that we're trying to work out. We can take this thing and say that time is distance divided by velocity. I'm doing these all longhand like this, not putting in symbols, but if you saw this in symbols, it'll be T is D over V. And up here it'd be D is VT. So the time that we want is just going to be plugging in these numbers that we've looked for. And so we'll have 778.3 times 10 to the 6 kilometers divided by 3 times 10 to the 5 kilometers per second. And this will give us something. What we'll eventually have is 1 over seconds. These kilometers cancel. And this is just some number of seconds. Don't know what it is yet. You should have a calculator, and you should know how to use it at this point in your classes. I cannot imagine a sequence of classes where you don't have a calculator that works, and this is the one I like. Right. So if I want to add 10 to the 6, it's going to be this EXP button, which I'll show you how that works. 1 to the 3, 1 exponent 3. All right, this is saying I want to write a thing like this, and this says I want 10 to the some exponent. And that should be 1,000. That makes sense. It's 1 and 3 zeros. So I want to plug this in. 778.3 times 10 to the 6. And now I want to divide. And you notice it gave me this number, and I can check that makes sense. I should have 7783 and 5 zeros. I have 7783 and 5 zeros. And I want to put in 3 times 10 to the 5. And this is what I should get, is 2594, and we'll ignore the fractions of a second. And then we'll look at this. Now, when you deal with significant figures, this is 4 significant figures, right? Because that's the 4 that's given in this scientific notation. This one's 1, but it is a constant. It is absolutely an exact number that we rounded. So we could round this to some amount, whatever we would like. But what this really is 299,792.5 about kilometers per second. So anyway, we got this number, right? 2594. Now we need to convert this to a reasonable time. How many minutes is that? So our time is 2594 seconds. And we want to convert to minutes. So we put a minute in. And 1 minute is 60 seconds. And so that means we're going to divide by 60. And so we take our number, keep it the way it is, and just divide by 60. And we get 43.2 minutes. And that's good enough on our calculation. Now, yeah, I've written a lot of stuff down here, but I've written it so you can see it, not because this takes that much time. If you want to do this yourself, you write down this, you write down the formula you're using, you write down your other constant, you write out the calculation, and you write out this unit conversion. And that's pretty easy. And now, if you want to know if it's right, you go look it up. And when I looked up Jupiter light travel time, I got about 43 minutes, but it does vary because the distance from the sun to Jupiter varies. So the range is like 35 to 52 minutes. But anyway, this is a good, nice round number. So if we're doing this, the distance to Earth is about 8 minutes, and that's 1 astronomical unit. To Mars, it's about 1.6 AU, and that's 1.5 times. You can estimate it as 13, 14, 15 minutes. And then to Jupiter's 5 AU, so 5 times 8 is about 40 minutes. And so these things make sense. And if you just follow these instructions, it's no big deal. But you have to be careful that you're doing your units correctly. Now, the other sort of problem that we have, all right, this is the chapter 2 stuff. We're looking at angular distances and angular sizes and such. And so we have this formula for it that is really kind of awkward. Our angular distance looks like 360 over 2 pi. So this is just a unit conversion. We're going to do everything in degrees. And then we have physical size over distance. Now, in your math classes, you may have seen this. And if I draw in an arc like this, part of a circle, there's the radius r, and we'll put in theta here, and this arc length is s, and these things are related. S is r theta. That's all this is. Our arc length is our physical size, and our distance is the radius. So this is s over r times a unit conversion is theta. It is our angular distance. That's all it is. And all we're doing here, this is saying that theta is in radians. And so this is radians to degrees. And it's 360 over 2 pi. Or it's 180 over pi, because you can simplify that. So we're going to look at, I will give you one of the calculations in number 12. I'll talk about the size of the moon at its closest distance. So if we're going to do this, we go look up those numbers. And so the moon size is what I told you in the homework. And this is the diameter. So this is the thing, it's the physical size, the diameter of the moon. I'm sorry, that looks horrible when I wrote it out. And the distance is, when I look this up, it is 356,400 kilometers. Right? And so what we're going to do is plug this in to get the angular size. And so when we do that, we'll have angle is 360 over 2 pi. And then we'll have our physical size is 3,476 kilometers over 356,400 kilometers. And now when you go to calculate this, what I'm going to do, clear my last result, I'm going to do the thing in parentheses first, and then I'm going to do this unit conversion. So we do 3,476 divided by 356,400, and we get some very small number, which makes sense. This is not a big thing. And then we'll go and do times 360 divided by 2, and then we're going to divide by pi, and I have a button for pi. And that gives us 0.5588. And I want to keep 4 sig figs because everything that I have that I looked up is 4 sig figs. And I need 4 sig figs to compare all these numbers. Now, what this is, since we did a unit conversion here, this is 360 degrees divided by 2 radians. Don't lock, computer, don't lock. So the thing in here, a radian is just a division of distances. So this actually cancels all this stuff out. We're left with degrees. Now, if I want to know what this is in other units, I'm going to do a unit conversion. 0.5588 degrees times 1 minute. Sorry, so I have 60 minutes over a degree. All right, so if I want to convert to minutes, I have to put in however many minutes I'm going to have on top, and then the 1 degree on the bottom to cancel it. Let's multiply by 60, and this is 33 arc minutes, 0.5. And then we can do the same thing, is 60 seconds over 1 minute, and the minutes will cancel, and I'll have times 60, 2012 arc seconds. But this is the thing that you need. If you got this for all of them, that's it. Everything else is unit conversions. So they're odd unit conversions here in the sense that we're doing angles. But that's all it is. It's just we have units, we have relationships between them, And these are things that you should know from your math classes. So the trickiest bit is looking this stuff up, and I gave it to you. It's in the problem. All we have to do is do this for the, in this one particular problem, we do it 4 times. Do it twice for the sun, we do it twice for the moon, and for each one of those, we do it at minimum and maximum distance. And you get 4 numbers. And so you're asked in the problem if it's both at the maximum distance, is there a total solar eclipse possible? And so that means, can the moon cover up the sun? Which implies something about these distances. So you also have a number 11, which is asking you about the angular size, or talking about the angular size of a star, and it works the problem in reverse. Right. So we can do this problem in reverse if we want. We're going to have a number in arc seconds, and I showed you what that was. So for the moon, the angular size we got was 2012 arc seconds. And the goal is, in the problem, to get the diameter, the physical size. And our distance is, well, when we're given it in a problem, it's in light years. And we need some sort of conversion for that. And we can put it into this problem. All right, we had 3476 times, 3476 kilometers, and we're going to divide by a number that we look up, the length of a light year. And when we look up the length of the light year, if I can find it, 1 light year is 9.46 times 10 to the 12 kilometers. So we're going to divide by 9.46 times 10 to the 12. No, 3476 divided by 9.46 times 10 to the 12. We'll get 3.67 times 10 to the minus 10 light years. I'm doing this in analogy to the problem you actually have. You have the same types of units here. And so we're going to use the same formula. We have angular size is 360 over 2 pi times physical size over distance. And so now we're going to rearrange to solve for the physical size. So physical size is 2 pi over 360, because what we're going to do is multiply both sides by this. So 2 pi over 360 and 2 pi over 360. And then the 360s cancel and the 2 pi's cancel. And then we're going to multiply both sides by distance. So we'll have angle times distance. And then we can put in our numbers. 2 pi over 360. Our angular size is, well, we're going to have to convert this. 2012 arc seconds times, and then we want to know how many, so we'll have 1 minute. So what we want is 60 seconds times 1 degree is 60 minutes. And then we're going to put in our distance. So I'm just going to put an X here. All right, so this continues on. And our distance here is this 3.67 times 10 to the minus 10 light years times, well, 1 light year is some distance, and we look it up, and it's 9.46 times 10 to the 12 kilometers. All right. So we're going to multiply all this out, and we can simplify a little further. 2 pi over 360. The first thing in parentheses is just undoing the thing we did in this problem. It's 0.5588 degrees. But if we want to calculate it, we do 2012 divided by 60, and we divide by 60 again, and it's 0.5588 and a bunch of other stuff. So this would be like a 9 at the end, but that's fine. And then this thing is just undoing what we did before. So it should be 3476. Nope. I used the wrong one, didn't I? I used 3476 to get that. But we'll do this calculation anyway. All right, so we'll do 3.67 times 10 to the minus 10. And then we will multiply by 9.46 times 10 to the 12. And I did it wrong, so we'll do it again. 3.67 times 10 to the 10 negative. All right, note the negative sign. You got to put that in. Let me zoom in a little bit. There we go. So 3.67 times 10 to, the negative 10. Put in the number first and then use the negative, or if you have a TI-83, you go the other way. And we'll multiply by 9.46 times 10 to the 12, and we get 3472 kilometers. And we're going to multiply this out and see what it is. So now I realize that I did something dumb here. What I did is I put the moon's distance as this 3472 when it's actually its size. So when we calculate this out, what we're going to get is how big an object would you need in space this far away to get something the size of the moon. Anyway, so we have that times 0.5588 times 2 times pi divided by 360. And what we get is you would need something 33.8 kilometers big. And I'll zoom that out. I wrote that down. So what we're saying is we want something that has this angular size, and it is 3470 kilometers away. It would have to be 4 kilometers big. Anyway, that one was kind of disastrous in a sense. It shows you how to do the calculation, but you don't know why you're doing this calculation because I used the wrong number. That's okay. So for those problems in chapter 2, it's all about this equation, and it all looks like the thing you did in math, and it's just about finding the numbers which I give you in both problems and doing the unit conversions for these. And so you want to remember is 1 light year is 9.46 times 10 to the 12 kilometers. And I often like to say it's 10 to the 16 meters, right? Because you'll convert that to meters, and then you'll round that to 10. It's 10 to the 13 kilometers. And then C is 299,792 kilometers per second. And then all of these things where you're converting 1 degree is 60 minutes, and 1 minute is 60 seconds. And they're arc seconds. Right? So you have all this stuff. Those are the 3 calculations you got. I hope this is enough. It's 25 minutes of video. If you have questions, please email me. Otherwise, we're going to let this go.